Okay, so now we're going to do the element method of proof, right? So we've done the Venn diagram method of proof. Now I'm going to leave the Venn diagram up here because it makes it a lot easier to understand what I'm talking about. But the element method of proof is essentially something like, if I'm going to say that set A equals set B, then what I'm really proving is if X is a member of A, then X must be a member of B. And if you recall, that proves that A is a subset of B. Then we prove if X is a member of B, then X must be a member of A, which proves that B is a subset of A. So if A is a subset of B and B is a subset of A, then they must be equal, right? This is the element method of proof. So let's drop in with a specific example. Let's say that P minus Q intersection with R minus Q is equal to P intersection R minus Q. Now, that might be a little bit intuitive if it looks very similar to the distributive rule. It is the distributive rule. It's just we're using minuses, so we would have to convert that to the other way of indicating subtraction, which is the and complement, which we talked about earlier. And then we could algebraically prove this, but we're not going to algebraically prove this. We're also not going to prove it with the Venn diagram, which we easily could. So if you look up in the Venn diagram, P not Q is going to be 4 and 7. R not Q is going to be 7, 3. Intersection, and it together, we get 7. On the other side, on the right-hand side, if we look, P and R is 8 and 7. Not Q removes 8, so that is also 7. So we could prove this with the Venn diagram as well, and in fact this one's a lot easier to prove with a Venn diagram. But we're going to use the element method because, well, we just are. Okay, and remember the element method says if X is a member of this set, then X is a member of P, but not a member of Q, and X is a member of R, but not a member of Q. Therefore, X must be a member of, well, what we just said, right? A member of P and R, but not a member of Q. Which is a little trivial because I just explained it to you with the Venn diagram, but, you know, if you said this with words, that would make sense, right? X is a member of P and a member of R, and X is not a member of Q. That is the one-way implication. The implication the other way, to draw a true element proof, we now need to prove if X is a member of P and R minus Q, then we need to prove it the other way. And again, it's pretty intuitive. X must be a member of P minus Q because it is a member of P and not a member of Q. X must also be a member of R minus Q because it is a member of R and it's not a member of Q. Therefore, X is also a member. Oh, I forgot to put that. I'm going to do a weird, but you get the idea. So that's an element proof, right? We prove if it is a member of one, it must be a member of the other. In this case, we did it using words, because that is the easiest way for us to do this element proof. You can also do a mixture of proofs, right? So we could have done some Venn diagram, some some algebraic manipulation, and then based on the algebraic manipulation, we can, do an element proof. But an element proof is a basic tool that comes up a lot. It's actually not used so much in set theory. In set theory, we tend to use the Venn diagram or the algebraic manipulation, but it's used a lot for proving other things with sets. I prove if this is true for this, then it must be true for that, and that's how we prove equivalence with a lot of other things. So I hope that explains what an element proof is. If you have any questions, ask them in the forum below.